Welcome to the Deep Dive, the show where we dive into a massive pile of source material, all the research, the engineering blogs, the internal papers, and we pull out the absolute essential knowledge for you. It's your intellectual shortcut. And today, we are tackling something truly, mind-bending. We're going deep on the engineering that powers our world, billion user scaling.
It really is the ultimate challenge for an engineer. And when we say scaling, we're not talking about, upgrading a small business website.
Right.
This is a totally different universe. We're talking about going from serving maybe thousands of people on one machine to serving billions of people.
All at once.
Simultaneously across the entire planet, and they all expect it to be instantaneous. It fundamentally changes what a computer problem even is.
And just to set the stage for you to really get your head around it, the numbers we pulled from the sources are. They're just staggering. Take Google.
Yeah.
They process over 8.5 billion searches every single day. That's an incredible amount of real-time data.
Or look at social media. Meta serves what? Over 3 billion active users a month? Every time you scroll, every click, every single interaction, that's a new computation, a new piece of data.
And then you have the content. YouTube, our sources say it handles over 1 billion hours of video watched daily.
And that's not just, sending a file. It's transcoding, it's metadata, it's recommendations.
And don't even get me started on the commercial side of things. Think about Amazon on Prime Day. We're talking about millions of orders, all financially sensitive, all happening in this tiny high-pressure window.
The tolerance for any kind of failure there is basically zero.
Exactly.
Let's just do some really simple back-of-the-envelope math here. If you have 1 billion users and they each do just 10 simple things a day, refresh a page, click a button, that's 10 billion requests every day. If you average that out, it's over 115,000 requests per second.
Wow. On average.
On average, and we all know traffic isn't average. It spikes in the morning and the evening when there's a big news story. So that number could easily jump to 500,000, maybe 1 million requests a second, instantly.
And that, I think, perfectly sets up the core problem, the thing that forced this entire revolution in engineering. Traditional architecture just breaks. It fails catastrophically.
It does. There's this very human instinct, right? Your server gets slow, so you just
buy a bigger one.
Exactly. You buy a bigger one. That's called vertical scaling. More CPUs, more RAM. You scale up. But you very quickly run into hard physical limits.
You can only build a computer so big.
You can't. There is no single computer on Earth, I don't care how much it costs, that can store petabytes of data and serve 1 million requests per second with the kind of latency users expect. A really high-end database server might top out at, 10,000 queries per second?
If you're lucky.
Yeah. But these companies need to handle 10 million. So the single server model, the monolith, it just hits a wall and completely falls over.
So that's the big shift. The whole paradigm changes. If you can't build a bigger boat,
you have to go horizontal.
You need a fleet.
You need a massive fleet. Horizontal scaling is the absolute non-negotiable core principle of all of this. It's the idea of taking the entire workload and spreading it out across thousands, maybe millions, of cheap commodity machines.
And they all have to work together perfectly.
In perfect concert. It's the foundation that everything else is built on.
Okay, so that's our mission for this deep dive. So we're going to unpack those core architectural principles, look at the crazy infrastructure innovations they had to invent, and dig into the operational secrets that keep these things fast and, not on fire. We're going to take you from a single server to a global self-healing network.
Yeah.
So if the answer is to spread the work out, the very first thing you have to do is, break the work up into smaller pieces.
Exactly.
And that brings us to the first big idea, microservices architecture.
And this is something that all the big tech companies did. They had to. They moved away from that giant single application, the monolith, where user login and search and payments were all tangled together in one code base.
Right.
And they broke it down. They decomposed it into hundreds, sometimes thousands, of tiny independent services. Each one does just one very specific job.
And this leads to this incredible complexity behind what seems like a really simple action. Our sources point to Netflix, to the classic example. You click play on a movie.
And behind the scenes, you've just kicked off an orchestra of over 700 microservices.
700? That's amazing.
It's a whole choreography. The second you hit play, dozens of services jump into action. One service checks your login credentials.
Authentication.
A totally separate one checks your subscription status. Another one looks at your location and your internet speed to pick the right video quality. At the same time, a logging service is recording that you started watching, which feeds the recommendation engine later.
And then finally, a different service actually starts streaming the video.
Exactly. And that whole complex dance gives you three massive advantages that a monolith just can't compete with. The first one is all about efficiency and cost, independent scaling.
Okay, what does that mean?
With a monolith, if your recommendation engine was getting hammered with traffic, you had to scale up the entire application, even the parts that were just sitting there, not doing much.
Wasting resources.
Totally. With microservices, you only scale what you need. The authentication service is pretty simple, right? Maybe it only needs 50 servers. But that recommendation engine, with its heavy machine learning models, it might need 5,000 servers. You can be surgical with your resources.
And the second big win is for the user experience, really. It's about resilience, failure isolation.
This is huge. If the microservice that handles, say, the comment section has a bug and crashes...
It doesn't take the whole site down.
No, it only affects the comments. Your video keeps playing, your recommendations still load, the billing service is fine. One broken piece doesn't cause a total system collapse. It's designed to survive partial failure.
Okay, but hold on. Breaking everything into 1,000 little pieces, that sounds like a nightmare to debug. I mean, if one simple action, like adding something to a shopping cart, touches 15 different services, how do you even figure out what went wrong when one of them fails?
You've just hit on the single biggest downside of microservices. It's the essential trade-off. The complexity doesn't go away, it just moves from the code itself into the network between the services.
So you need new tools.
You need incredibly sophisticated tools for what's called distributed tracing. Systems that can follow one single request as it hops between all 15 of those services, measuring the time it takes at every single step. It's a massive investment in monitoring. But it's worth it for the third advantage, speed of development.
The organizational speed.
Absolutely. You can have small, focused teams that own their one little service. They can build it, test it, and deploy it multiple times a day. They don't have to wait for some huge quarterly release that has to be coordinated across the entire company. It lets them move incredibly fast.
So microservices break up the logic. But all those little services still need to remember things about the user, right?
Yeah.
Which brings us to this idea of stateless services. It sounds a bit abstract, but it's crucial.
It is the absolute key to being able to scale up and down instantly. A stateless service is one that doesn't hold on to any user information locally. It doesn't remember your user ID or what's in your shopping cart on the specific server that's handling your request right now.
So where does all that state go?
It gets externalized. It's pushed out into a shared storage system that all the services can access. This could be a super fast in-memory cache like Redis or a specialized database just for session data.
So the service grabs the data it needs, does its job, and then just forgets.
It completely forgets. It's like a worker with short-term memory loss. It handles the task and is immediately ready for a brand new, unrelated task from any other user.
And why is that so important, that sort of architectural amnesia?
It makes every server instance interchangeable. That's the magic. If every server is identical and stateless, any one of them can handle any request from any user. So if the server you were just talking to suddenly crashes,
your next click just goes to a different one.
a different, healthy one. It pulls your session info from that shared storage, and you, the user, don't notice a thing. There's no interruption. That seamless failover is fundamental.
Let's bring that back to the Prime Day example.
Yeah.
The huge, sudden traffic spike. How does being stateless help there?
It's what allows them to absorb that load. Amazon will use predictive models to guess how much traffic they'll get, and they'll prescale, adding thousands of extra servers in the days leading up to the event.
Okay.
But when that 10x spike hits the second the sale starts, they can just instantly route that flood of new requests across this massive pre-warmed fleet of interchangeable servers. There's no complicated process to hand over user sessions. They just use the capacity that's sitting there ready to go.
And as soon as the spike is over, they can just turn off 80% of those servers and stop paying for them.
Exactly. The system is elastic. It can grow and shrink instantly to match demand, which is not only essential for reliability, but also for managing the insane cost of running all that hardware.
Okay, so we've broken up the application logic with microservices, and we've made the compute layer elastic with stateless design. Now we come to what is, I think, the biggest bottleneck of all: the data itself.
The database.
A single database server just can't hold petabytes of data or handle millions of queries a second.
It can't, which is why sharding becomes absolutely essential. Sharding is just a fancy word for breaking up one massive logical database into hundreds or thousands of smaller, physically separate databases called shards.
So Facebook's 3 billion users aren't all in one giant spreadsheet.
Not even close. That one logical table of users is actually broken into, say, 1,000 smaller tables, each on its own database server.
And how do they decide who goes where?
Ah, the sharding strategy is incredibly important and depends on how you access the data. For something like user profiles, you might shard by a simple range of user IDs. So users 1 to 10 million are on shard A, users 10 million to 20 million are on shard B, and so on.
Makes finding a specific user really fast.
Very fast. But what about something like posts? Sharding by user ID isn't great there, so you might shard posts by date, so all the newest posts are always being written to the current hot shard. For relationships, the friends data, you'd probably use a hash function to spread the data out evenly.
And our sources kept bringing up Instagram and their use of Cassandra.
Yeah, Cassandra is a perfect example of a database that was built from the ground up for this kind of scale. It's a NoSQL database. Instagram uses it to spread all their data photos, likes, user info across thousands of nodes all over the world.
And it handles reliability automatically.
That's its superpower. It automatically replicates every piece of data onto multiple machines. So if one server fails, the data is safe on another, and the system can keep serving reads from one of the healthy copies.
But you touched on the downside before, and I want to go back to it. This sounds incredibly complicated when you need to pull data from multiple places. Like, building my news feed seems impossible if my friend's data is scattered across 50 different shards.
That is the fundamental challenge of sharding. To build your feed, the application has to send out queries to dozens, maybe hundreds of different shards to collect all the posts from your friends.
A fan out.
It's a massive fan-out query, and it requires a really sophisticated coordination layer in the application to manage all of that.
And all those separate network requests must add a ton of latency, must be slow.
It would be unusably slow.
Yeah.
If not for caching. Sharding is a complete failure without a massive, aggressive caching layer sitting in front of it. Sharding solves the storage problem, but it creates a huge network problem. And you solve that network problem with caching. It's this constant balancing act.
Okay, so if the last segment was about organizing the software, this next part is about the actual physical and virtual metal that makes it all run.
Exactly. This is where we talk about the global foundation, and it's where these companies had to literally invent new solutions because the off-the-shelf stuff just couldn't handle the load.
And the first problem is just getting the traffic in the front door and sending it to the right place. Load balancing.
At this scale, load balancing isn't one device, it's a multi-layered system. You have to be smart about distributing traffic at every single step of its journey.
So let's start at the very edge of the internet.
The first layer is DNS. When you type in a website, the domain name system doesn't just give you an IP address. It gives you the IP address of the data center that is geographically closest to you.
So it's a very basic first-pass load balancer.
Right. It's the simplest, cheapest way to shave hundreds of milliseconds of latency right off the top.
Okay, so my request hits the nearest data center. Now what?
Now you hit the big iron, the hardware load balancers. These are specialized boxes that can handle millions of connections at once. Their job is to spread the requests evenly across the thousands of web servers inside that data center, and they use some clever algorithms to do it, the most important being consistent hashing.
Why is that better than just, a simple round-robin approach?
A simple approach is brittle. Imagine you have 100 servers. If you add one more, server 101, a simple hashing algorithm would force you to reroute almost all of your existing traffic to maintain an even spread.
Which would invalidate all your caches.
Exactly, a total disaster. Consistent hashing is a mathematical trick that minimizes that disruption. When you add or remove a server, only a tiny fraction of the traffic needs to be rerouted. The rest of the system stays stable.
So it's about minimizing turbulence. Okay, so now the request is inside the application. There's another layer of routing, right? The service mesh.
Yeah, this is the traffic cop inside the data center. Technologies like Istio or Linkerd manage the traffic between all the different microservices. It's constantly watching the health of every single service instance. So if service A needs to talk to service B, the mesh makes sure to send that request to the healthiest, fastest responding copy of service B.
And this is another area where the scale got so extreme they had to build their own hardware. The sources talked about Google's maglev.
Maglev is just an incredible piece of engineering. Google built it because no commercial load balancer on the market could keep up with their search traffic. It's a custom piece of hardware and software that can handle millions of requests a second with latency measured in microseconds. It just shows that at the very top end, you have to control the entire stack, from the silicon up to the application.
Okay, so even with all that, the speed of light is still a thing.
Oh.
A request from Tokyo to a server in Virginia is going to be slow, no matter what.
Right. The only way to beat that is to move the data closer to the user. And that's the whole point of a content delivery network or a CDN.
This is for all the static stuff, right? Images, videos, code.
Exactly. A CDN is a global network of servers that caches copies of that content in hundreds or thousands of locations worldwide. So when you load a web page, the images don't come from Virginia, they come from a server that might be in your own city.
Which turns a 200 millisecond delay into a 20 millisecond one.
Or less. It's the difference between a site feeling sluggish and feeling instant.
And of course, Netflix, with their massive video files, took this to the absolute extreme with their own custom CDN Open Connect.
They had to. They weren't just serving little image files, they were pushing enormous continuous streams of data. So they built their own CDN with over 18,000 servers in more than 1,000 locations. And here's the clever part. They often put these servers directly inside the networks of the big internet service providers.
So when I'm watching a show, that data might be coming from a box that's literally down the street from my house.
There's a very good chance it is. It's probably not crossing an ocean or even the country. It's coming from your local ISP's facility. This massively improves streaming quality, especially for 4K video, and it saves Netflix an absolute fortune in bandwidth costs they would otherwise have to pay.
It's horizontal scaling, but for the physical world. Now, this is evolving beyond just caching static files into what's called edge computing.
Edge computing is the next logical step. It's the idea that you don't just have to store static files near the user, you can actually run code there. Platforms like Cloudflare Workers let you run little bits of logic at these edge locations.
So, like, a simple check to see if my login session is still valid could happen 20 miles from my house instead of 2,000 miles away in a central data center.
Precisely. It lets you build dynamic, personalized applications that feel as fast and responsive as a static website. You're basically moving the computation out of the data center and pushing it to the very edge of the network, as close to the user as physically possible.
Okay, so we've established that the old-school relational databases just couldn't keep up. This forced the big players to invent entirely new kinds of databases. Let's start with what might be the most ambitious of them all. Google Spanner.
Spanner is wild. It's a database that is spread all over the globe, handles millions of transactions per second, and, here's the kicker, it provides strong consistency.
And strong consistency means that no matter where in the world I am, if I read a piece of data, I am guaranteed to see the absolute latest version of it.
Always.
How is that even possible when the data centers are thousands of miles apart?
This is where it gets crazy. They solve this software problem with hardware. In every single one of their data centers, they have installed their own atomic clocks and GPS receivers.
Wait, really? Actual atomic clocks? Like physics-level precision instruments?
Yes. They built a system called TrueTime that uses these instruments to make sure every server on the planet has an incredibly precise, synchronized sense of what time it is. They use these timestamps to order every single transaction globally. It allows them to provide the same guarantees as a traditional single-server database, but at planetary scale. It's an insane engineering feat.
An advantage that almost no one else can afford to replicate. Okay, now let's talk about Amazon's big one, DynamoDB.
So DynamoDB comes from the other side of the fence. It's a NoSQL database built for basically infinite horizontal scaling. But it makes a different trade-off. It prioritizes availability over that strong consistency that Spanner provides. We'll get into that trade-off later.
And the numbers for DynamoDB on Prime Day are they're hard to believe.
They are the ultimate proof of its design. The sources said that during Prime Day 2023, it peaked at 105.2 million requests per second.
Wow.
And it handled that fire hose of traffic while keeping its latency in the single-digit milliseconds. It's a system that is built to just absorb punishment at a scale that's almost incomprehensible.
And briefly, there's also Facebook's contribution, RocksDB.
RocksDB is a little different. It's not a full-blown database service like the others. It's an embeddable storage engine. It's a super fast, low-level component that's optimized for modern flash storage, like SSDs. Facebook uses it as the foundational layer for a lot of their own high-performance internal systems. It's one of those unsung heroes that makes everything else possible.
So we have the architecture, we have the global infrastructure, but even with all that, these systems would still collapse under the load without some very clever operational tricks.
Mm.
And if sharding is what keeps the data from overflowing, caching is what makes it all feel fast.
Caching is, without a doubt, the single most important optimization in any of these systems. If every single request had to go all the way back to a sharded database, the whole thing would just grind to a halt. Caching is the shield that protects the database. It intercepts the vast majority of requests and serves them instantly.
And as we talked about, it's not just one cache, it's layers of caches.
Right. It starts on your device, your phone, your browser. They all have a local cache. That's layer 1. Layer 2 is the CDN, caching all the static assets globally.
But the real magic happens at layer 3, the application cache.
This is the big one. These are huge distributed systems like Redis or Memcached that run entirely in RAM. They sit between the application servers and the databases. And because they're in memory, they can serve data back in microseconds. That's orders of magnitude faster than a database that has to read from a disk.
And the gold standard example here is Facebook's cache for their social graph called TAO.
Yeah, TEO, the Associations and Objects, is a custom-built caching system of monumental scale. Its entire job is to store a copy of the social graph, who is friends with whom, what posts they've liked, in memory, ready for instant access. It's what makes building your newsfeed possible.
And the performance numbers on this thing are the key to the whole operation.
They really are. TAO handles billions of reads per second, and for the most common requests, its cache hit rate is consistently over 99%.
Okay, let's just pause on that number for a second. A 99% hit rate means that for every 100 times the application needs a piece of data,
99 of those times, it gets it in microseconds from the RAM cache.
only one time does it have to do the slow, expensive trip all the way back to the actual database.
And that is the secret sauce. That is the economic and technical trick that makes the whole thing work. The system is designed with the assumption that the database will almost never be touched for reads.
But that raises a big question. How do you keep the cache up to date? When data changes in the database, how do you get rid of the old, stale data in the cache?
That's the hard part. It leads us right to that famous quote from Phil Carlton.
There are only two hard things in computer science: cache invalidation and naming things.
Exactly. And cache invalidation is hard because of the sheer scale. When you change your profile picture, that old picture might be stored in caches on hundreds of servers across 4 different continents. How do you tell all of them instantly that their copy is now wrong?
So what are the main strategies they use?
Well, the simplest one is just time-based expiration. You tell the cache, this piece of data is only good for 5 minutes. It's simple, but it's not very efficient.
Right.
A smarter way is using event-based triggers. When the data is updated in the database itself sends out a little message, an event, that tells the relevant caches to delete their old copy.
And the third way is versioning.
Yeah, you just attach a version number to every piece of data. When the application asks the cache for something, it says, hey, give me the user profile, but I need version 7. If the cache only has version 6, it knows its copy is stale, and it needs to go get the new one from the database.
The Twitter example really drives home how hard this is. When someone with millions of followers sends a tweet,
You can't possibly update the timelines of all millions of those followers in real time. The amount of network traffic that would generate is it's impossible. It would break the system.
so they have to make a trade-off.
A very conscious one. They accept what's called eventual consistency. The tweet gets delivered to your followers' timelines asynchronously over a period of a few seconds, maybe even a minute. They sacrifice that instantaneous, perfect consistency in order to keep the entire service available and not crashing.
So we know these massive traffic spikes are going to happen. And you said that just relying on standard autoscaling is too slow. It can't react fast enough.
It can't. Waiting for your CPU to hit 70% for 5 minutes before you add new servers. By then, it's already too late. The fires are already burning. For these big planned events, you have to use predictive scaling and pre-warming.
What's the difference between those two?
Predictive scaling is long-term. You use machine learning on historical data to forecast the traffic for an event like Prime Day, and you start adding capacity hours or even days ahead of time. Pre-warming is the short-term tactic. You maintain a big buffer of servers that are fully configured and running but are sitting idle,
Ready to go.
ready to go at a moment's notice. The second that traffic wave hits, you can instantly activate that buffer and absorb the initial shock.
And that buffer is what prevents the ultimate nightmare scenario. The cascading failure.
The cascading failure is what keeps engineers up at night. It's when one small service gets overloaded, say the login service, and starts to slow down. Then all the other services that depend on it start waiting and waiting.
And they start to fail.
And they fail, which then causes the services that depend on them to fail. It's a domino effect that can take down the entire platform.
And the tool they use to prevent this is the circuit breaker.
It's named after the electrical device in your house. It's a piece of code that monitors the health of the services it calls. If it sees that a service is failing too often or is too slow, the circuit breaker trips and stops sending any more traffic to it for a little while.
It gives the failing service a chance to recover.
Exactly. It sheds the load. And this is where Netflix's Hystrix library was so influential. It popularized this pattern.
So what does the user see when a circuit is tripped?
They experience what we call graceful degradation. So if the recommendation service is failing and its circuit breaker is open, you don't get a big, ugly error page. Instead, the application falls back to a default. Maybe it shows you a generic list of the top 10 movies, or maybe that part of the page is just blank for a minute.
You prioritize the core function.
Always. YouTube will make sure your video keeps playing, even if the comments and the live chat break. The core experience must be protected at all costs, even if the secondary features are temporarily unavailable.
Which brings us back around to this fundamental law of distributed computing, the CAP theorem. It's like the laws of physics for these systems. You can't escape it.
You can't. It is the inescapable reality check.
So just to review, the three properties are consistency, availability, and partition tolerance.
Right. C, A, and P. Consistency means everyone sees the same data at the same time. Availability means the system always responds to a request. And partition tolerance means it keeps working even if the network breaks between data centers.
And since network partitions are just a fact of life,
P is not optional. You have to design for it. So the cruel choice that the theorem forces on you is between C and A. You can have a consistent system or you can have a highly available one, but you can't guarantee both during a network failure.
so the choice really comes down to the business need.
Entirely. If you're building a banking system, you have to choose consistency. You can't have a situation where two people see two different account balances. But if you're building a social media feed,
You choose availability.
you choose availability. It's okay if it takes a few seconds for my friend's new post to show up for everyone. It's not okay for the entire site to go down because one network link is flaky.
And Facebook's profile updates are the classic example of this.
That's the textbook example of eventual consistency. You update your profile, and that change gets written to the main database. Then, over the next few seconds, that change gets copied out to all the replica databases around the world. In that tiny window, it's possible for some users to see the old data.
But it's a trade-off they willingly make for performance and uptime.
A necessary one. And what about when you have multiple people trying to change the same thing at once, like two people adding items to a shared shopping cart from different devices?
How do you resolve those conflicts?
You use some clever data structures called CRDTs, or conflict-free replicated data types. They're designed in such a way that no matter what order the updates arrive in, they will always merge together into the same correct final state.
So in the shopping cart example, the system knows how to merge the two additions together, so the final cart has both items in it, instead of one change overwriting the other.
Exactly. It avoids the need for a central coordinator to lock the data, which would kill performance and availability at scale.
Okay, so we've covered the tech, the architecture, the operations. But building these systems isn't just a technical problem, is it? It's also a human problem.
It is fundamentally an organizational and a cultural challenge first. And this is where Conway's Law comes in.
Which states that.
Organizations design systems that mirror their communication structure. So if you have a slow, siloed, bureaucratic organization, you will inevitably produce a slow, siloed, bureaucratic piece of software, a monolith.
And to fight that, you have Amazon's famous two pizza teams.
The rule is brilliant in its simplicity. A team should be small enough that you can feed the entire team with two large pizzas.
So 6 to 10 people, maybe.
Exactly. And these small, autonomous teams own their microservice from beginning to end. They write the code, they deploy it, they monitor it, and, this is the crucial part, they are the ones who get paged at 3 a.m. when it breaks.
And that complete ownership is what drives quality.
It creates a powerful feedback loop. If you know you're the one who has to fix it when it's broken, you are highly motivated to build something that is reliable, well-tested, and easy to maintain. It gets rid of that old us versus them mentality between developers and operations.
To move at that speed, you also need to completely automate your release process. This is where continuous deployment comes in.
It's mandatory. Companies like Facebook are deploying new code hundreds, if not thousands, of times a day. You can't do that manually. It requires extreme automation.
But that sounds terrifying. Pushing thousands of changes a day to a billion people seems incredibly risky.
The risk is managed through gradual rollouts. They'll use a technique like a canary deployment, where the new code is released to just a tiny fraction of users at first, maybe 1%.
The canaries in the coal mine.
Exactly. They watch the metrics from that small group like a hawk. Is latency up? Are error rates climbing? If everything looks good, they'll gradually increase the rollout to 10%, then 50, then 100. And if anything looks wrong at any step, an automated system immediately rolls the change back.
And this whole philosophy of treating operations as a software problem is codified in Site Reliability Engineering, or SRE.
SRE, which was pioneered at Google, is all about that. You put software engineers in charge of operations, and they automate everything. And a core part of the SRE culture is the blameless postmortem.
When something goes wrong.
The goal is not to find someone to blame. The goal is to deeply understand the systemic reasons why it failed, and then build the automated systems to make sure that specific failure can never happen again.
I think the most interesting part of SRE is the idea of error budgets. It seems so counterintuitive.
It's a genius concept. An error budget quantifies how much failure is acceptable. So if your service level objective is 99.99% uptime.
4 nines.
Right. That means you have an error budget of about 52 minutes of downtime for the entire year. And that budget gives the engineering team permission to take risks. They can move fast and try new things as long as they stay within their budget.
But if they use up that budget,
The hammer comes down. The rule is simple. If your team exceeds its error budget, all new feature development stops. 100% of your team's time must be spent on reliability and stability until you're back on track. It creates this perfect data-driven balance between moving fast and not breaking things.
okay, so looking to the future, we've sort of perfected this model of massive centralized data centers. What's the next frontier for scale?
I think the next big shift is about pushing the computation even closer to the user and abstracting away the servers entirely. We're talking about serverless and the edge.
Serverless, like AWS Lambda, where you just upload your code and the platform handles all the scaling for you.
Right. You don't even think about servers anymore. And edge computing takes that even further. The idea that your code might not run in a data center at all, but at the edge of the network, just a few miles from the user. The future of many applications might be running almost entirely on the edge.
And then there's the massive challenge of AI and machine learning.
Oh, that's a whole other dimension of scale. Just training a model like GPT requires a supercomputer's worth of hardware running for weeks. But then serving that model, delivering billions of recommendations or search results every day, is an equally hard scaling problem that requires its own specialized infrastructure.
And as Moore's law slows down, these companies can't just rely on buying faster generic chips anymore. They have to build their own.
That trend is definitely accelerating. You see Google with their TPUs for machine learning, AWS with their Graviton processors for cloud workloads. To get that next level of performance, you have to build custom hardware that is perfectly tailored to your software.
And finally, we have to touch on the environmental impact of all of this, the sustainability challenge.
It's a huge issue. Data centers now consume something like 1% of all the electricity on the planet. As these systems continue to scale, they have to do it responsibly. You see companies like Google using machine learning to optimize their data center cooling, which cut their energy use by 40%. That drive for efficiency isn't just about saving money anymore, it's an absolute necessity.
This has been an amazing look under the hood of a world that is, for most of us, completely invisible. We went from the limits of a single server to this idea of a global distributed fleet.
Mm-hmm.
And it feels like the big secret is this philosophical shift, embracing microservices, using stateless design for that instant elasticity.
And of course, the absolute non-negotiable power of caching. That 99% hit rate from systems like TAO is the linchpin that holds the whole thing together. And you have to be smart about the trade-offs, like the CAP theorem forces you to be. It really is just a testament to what engineers can build when pushed to the absolute limit.
So for you, the listener, I think the takeaway here is that to succeed in this world, you have to nail the fundamentals. You need to really understand algorithms, networking, and the theories behind distributed systems. Getting your hands dirty with open source tools like Kubernetes or Cassandra is where you start.
And as we finish up, the sheer scale of these systems, the fact that they touch billions of lives every single day, it brings up a final, I think, provocative thought for you to chew on. When a system reaches this size, the engineering problems start to become societal problems.
Mhm.
When your error budget can affect global communication or your recommendation algorithm can influence an election, how do you balance that relentless push for growth and reliability with the immense ethical responsibility that comes with that power? That's the real challenge for the next generation of engineers. How do you scale responsibly?